All right, so this is basically our answer for the search, which is the binary search, which is number 40 or 704. One line of code. Take the math max. Since our lowest number that we will accept as a return is -1 for when the variable is not found, and then we'll compare it with if the variable is found, so the index of. So if it's not found, it's always, the -1's always going to be greater, so then we'll return that. So when we submit, it took me a while to figure it out, see? So we are fastest, but we take space. I don't know how to make it not take space. All right, you got any questions on this one? All right, insert into the binary tree. Oh, please, let me. Put this in the chat for y'all. Wish that dash wasn't there, but it is. All right, insert into binary tree.
Whoa, jag fit.
701.
They're not allowed to do that. Online? How do you have an online jag fit event?
Oh, I don't know.
That sounds like not right.
All right, so if you are unfamiliar with the binary search tree, Dennis.
Me?
Definitely not.
All right, so the binary search tree, let me get my annotating pen out here.
Wait, didn't I already do this question? I think I did this question just like a week ago.
Good, then you should have the answer.
I think I had to look it up.
So this is the root of the tree, okay? So the root is, when you're looking at it in this fashion, is the tallest one on top. And it has two children. It has the left child and has the right child. The right child always in the binary search tree always has to be greater than the 4. And the 2 on the left-hand side always has to be less than 4. And you can follow the same trend down. So here on our second level, 2 is now our root, 3 is greater than 2, and 1 is less than 2. And you can see that same process here. So when we put 5 in, it goes over to 7. And if we were to put 4 in, we would come down here to 4 off of 3. Now, one of the key things that you'll probably never learn, Dennis, but about trees is that there's the binary search tree and then there's the balanced tree, and depending on what you're trying to do, one's better than the other, and they're confusing, and Ray can never remember when you rotate or which way to rotate. Remember rotating, Ray?
What now?
Where would you use these?
So trees are used, where are they most used?
Sorting.
So like if you were to construct like a an algorithm to actually do a search, you would build a tree out of that search to effectively do the search correctly. So if you could think of like Google is almost like a huge tree. I mean, they don't look like this obviously in real life, but the links are the links, because each one of these is a node. So there's a link. There's basically some little bits of memory here that are saying that this is linked to this and this is linked to here, and it's also saying where the where this particular node resides within the tree. So now you're making me, I'm going to Google.
Now go ahead and keep going.
Okay.
I kind of get the gist of it.
Yeah. I mean, a lot of these things you're probably not going to necessarily use a lot, but there are times when they actually do come up.
Kind of like algebra class.
Yeah. Yeah.
That you don't use.
You know, it's like, I don't know, calculus. I still don't know where calculus is going to come into play. When's calculus going to come into play for us, Ray?
Probably video games or like
Well,
very
that's more
complex mathematical computations.
Yeah, but I think a lot of, well, I guess when you start doing the big O and stuff, and the what were the other ones, the theta and the omega,
What now?
the big theta and the big omega. Remember
Yeah,
those
sure.
from algorithms?
Yeah.
Those were all calculus. But I think but like video games, a lot is going to be more of the linear algebra.
I think there's going to be a lot of like physics for like simulations. So like the arch of like movement of like gravity and stuff.
Oh, I see what you're saying. Oh,
It's
when
not just video games, but like simulations.
Okay.
So if you're testing like how well something is going to react in the real world, you probably need calculus to, prepare that environment.
Right. What just happened? I don't know what the hell's going on. Am I still sharing LeetCode?
Yep.
Okay. I want to make sure something just flickered on my screen. You never know what's going on. Okay. So in any case, the key pieces that we want to keep track of is what the value is that is going to be inserted into this tree. All right. And that value is going to determine where that particular node ends up getting put into. Okay. So if it's greater than the root, it's going to go to the right. If it's less than, it's going to go to the left. And then we'll test all the way until we find an empty position in the tree for it to rest. Does that make sense? Did I explain it better than that, Ray? I don't know.
I mean, I understand. I mean, I know what it is.
Okay.
Every time it's left, it's less than. Every time it's right, it's bigger than.
Okay. Yeah.
Why are you laughing?
No. It's just
No?
your Mr. I don't like binary search trees, and then
I don't like binary search trees because I can't figure. I couldn't do it when I looked it up. I had to look up the answer. I was so confused. I didn't know what I was missing or why it wasn't working.
All right, so we're gonna. So as we're doing our code here, we're gonna start off with a base case. Basically, if there's nothing in the tree, then we can just stick the new node in, right? Because the tree doesn't exist. If the tree doesn't exist, you have to quit, right? Something like that. I don't remember.
Base case.
Because we are going to recurse here, do some recursions. So we're going to return. Then we'll do the new tree node. That is going to be the value. Right? Yeah, need the value. So if there's no tree, we're going to put a new tree node and build the tree. Easy peasy. So quote unquote, we put our first node on, if you will. So if we were going to put other ones on, this is how we're going to add on to it. So we're going to start with the root and the value of root. So up here, there's a constructor built into the program behind this. If you are going to be doing a tree or anything with nodes, you'd have to build out your own nodes. That's not something that Java does automatically for us, which is kind of crap, I say, but whatever. So, but what we're looking at is the values. So the value is what the actual node is holding. So the circle is the node, the value is the floor. All right. So if we're going to go, and our initial is value, so we're going to test against val. So this is the value we're trying to input into the tree. So if it's greater than root, then we're going to go to the right. So we'll go root right. And now this is where we're going to start getting a little crazy, because we can't just stick it right to the right? Because, for example, if we're in number 1 and we're going to put 5 in there, 5 is going to go to the right, but then we have to test it also against 7. So how do we test it against 7? So we could do a loop here, or what's a better excuse than doing a loop here, Ray?
Recursion.
Recursion. So recursion is just, we're going to call the method within itself. So we'll kind of loop through the program or through the method. So right now, in this first iteration, we're taking in the root. So we have basically the tree is built up in here, and we're taking in probably in the main method the entire tree as is up here in example 1. Okay, and then the value. But we want to move away from, we're starting on 4 here, so we want to move to the left now over here, and, or yeah, to the right. So we want to now check the right to make sure. So we don't need to change anything necessarily besides root, except for we want to actually change that root to 7 now instead of 4. So we'll do that just by calling the same thing that we're calling this, right, and then we'll pass the value through. So what we're doing now is jumping down to 7. So if 7, let's say we're putting 8 in. This is a good example. So if we put in 8, let me get my pen. I don't know what I just did. I paused something. Trying to get my pen. All right, so let's put in, we're gonna put in 8. 8 is our new value. So we're gonna test against 4 first. So it's greater than, so we're gonna go to the right, and then we come here, right? And then we're gonna go to the right again. So basically what's happening is 8 comes in, all right? The root's not, the root is not null, so we're going down to this if statement here. And 8 is greater than 4, so we're gonna run through. So as we run through, now root is 7. Originally it's 4, now it's 7. And when we get here, well, the root's not, it's not null, and it's greater than, so we're gonna go through again. So we go through a second time, and we go through a second time, well, now it's null. Because there is no, this is empty, there's nothing here. So now, as we're at null, now we're gonna stick in the value of 8 in this new tree node that we created. So if we were to say, do 5, let me clear this out. So we put 5 in. So 5 is greater. So we're going to come down here. Our root starts with 4. Our value starts with 5. So we're not going to hit null. We actually have a root. So we're going to come down here. And we meet this first 4 and 5. So we're going to come back up here. But what we're taking now with us is 7. So now this becomes 7. And so we come down here, and now we have a problem, right? Because 7 is greater than 5. So we can't put it to the right. So now we have to actually build something for the left. So let's clear this out. So else root left equals insert into BST root left, comma val. All right. So now when we have 5, 4, 5, we start here, we end up here, we come through, this changes to 7, and now, because this doesn't happen, we go to else, and so we go to the right here, and we find that this is null, there's nothing here. This is now null. So then we put in the new value. So in this case, 5 goes there. And it'd be the same thing if we went, well, not the same travels, but if we put in other numbers in there. Because it's a binary search tree, we cannot accept other or duplicate values either. So and that will be cleared up. So we still need to return a value. So we're going to return, it has to be a tree node. So what we're going to return is just root, because root at this point is going to end up being the node where we stuck it. So if it was 5, for example, it would be back here. So that would be root at this point, because we've already gone down 2 and inserted it in. So because root is not null anymore, it's now equal to the 5. So if we run our code to test our code, so we should be accepting 5 in. Did that run? Just didn't run. So 5. So we're returning the entire tree node. So we're returning the entire tree. That was what came in here. So we actually added it to the new tree. So when you can think of this array, how the tree node's coming out. The 4, the 2, the 7, the 1, the 3, and the 5. So it goes through its breadth through the array. So it fills in from each line going from left to right. And you know which one's going to be broken up because it's kind of that pyramid of first line's going to be 1, second line's going to be 2, third line's going to be 4. So one of these is null. And it actually, the next set, which will be 8, is really null, 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 null. So if we submit, oh, slightly slower than last time. What's going on there? Does that all make sense, Ray, Dennis? I guess whoever's left here, Ray.
Oh, Dennis is gone. Yeah, sure. I was when I first did it. The reason why I looked it up was because I got to return new tree node on my own, but I kept running it and it didn't insert it because I didn't do root.right equals or root.left equals, and I was confused as to why that had to be part of it.
Yeah,
I wasn't really paying attention to how the recursion was working and how it needed to set that node to that value. That was what was confusing to me.
You understand it now?
Yeah, but I feel like if I did it again, or if I was asked a different question with the same sort of tree node class, I feel like I would get it wrong again because of that problem.
Oh, we'll check that out.
Oh, great. Except I don't know how long I'm going to be here until my mother breaks in.
Well, I mean,
Oh, yeah, look. You can't do it. Oh, never mind.
oh,
Oh,
oh.
I didn't look. I looked, I realized what was happening and I didn't look. But I do see like I noticed maximum depth. So that's probably like counting every time. Oh, wait, but there's no. Forgetting a bracket.
All right. So we're gonna do. I mean, we're gonna recurse again because I think everything with trees is recursion.
Yeah.
So we're gonna need the base case. The base case is gonna be exactly the same as before. So root.
Well, it's not going to return a new tree node. It's just counting.
No. Yeah, it's just gonna return 0 at this point because we're returning the integer.
Oh, I see.
Yeah.
I thought it was returning true node.
Yeah, it's returning an integer. So we're just counting down the depth of the tree. Okay. So we're end up doing this kind of the same. All right. We're going to do some recursions.
If root.val is greater than root.right.val, something like that.
Something like that. So we're just going to do, so we'll start with right like we did last time. So right is going to end up with max depth because we're recursion. So, but we're going to go roots right. And then we're going to, because what are we going to get there? We're just, all we're doing is getting 1. And then we'll go through again and we'll get to 2 or 3 or however many times we go through, that right will.
That's just going right as far as it can.
Yeah, actually we'll start with 0 and then go up, yeah. Because everything starts with zeros. And we'll also do the left side because you never know. So we'll go root to the left. And then we're almost done. So we just have one more line of code left. And we're going to return. All right. So what construction do you think we're going to use to figure out which is greater, right or left?
Max.
Max.
Well, isn't this just going to infinitely stick to the right side?
Why would it stick to the right side?
Or I mean, to the right or to the... Well, because what if like a node in the middle is... Or is that not how it works? No, that's not how it works, is it?
No.
I don't remember how tree nodes work.
Because we're not looping through it.
Well, because they don't have to be balanced, right? Or does a binary...
No, it doesn't have to be balanced.
So like because what I was thinking is like, say for example, there's more on the 15, like for that example.
Yeah.
But it wouldn't be.
If there was like
only
a,
sticking to the
like
right
a
or the left. Yeah.
No, it would go because it finds the 16. It finds the 15, doesn't it? Because it goes to the left.
Does it?
Hmm.
We
can put that as a test case. Okay. So if if we only have 3, what is it gonna? What is my value of int left and int right gonna be?
9 and 20.
No, if it's just 3. If all we have is 3,
Oh, probably 3 and 3.
no, it's gonna be 0 and 0
Oh,
because it's the max depth. We're just counting down through. So because it's 0, because it's like an array, we're gonna add 1. So now it actually is, if it's just 3, it'll be 1.
but the default values aren't 0.
It's the same thing as an array.
Hmm. Oh, I see what you mean.
Starts with it. The first row is 0, second row is 1. I don't know why computer programmers couldn't figure out that 1 is the first number. All right, so you wanted to say that, for example, if we had 16 in there, okay?
Mhm.
So let's go to our test case. We'll add it in. So we go null, null,
No,
null, null.
16.
Do you want a 14 or a 16? Which one do you want?
That's 14.
You want 14?
Yeah.
I have enough nulls in there. One more null.
No, I think that's it.
We'll find out.
Oh, maybe I miscounted whoops.
Oops. Seven, 1, 2, 3, 6, 8.
Or did you put the 4? Do you need to swap the left null and 14? The 14 and the null on the left of it? Oh, what did you got rid of a comma between null and 14?
Did I? Okay.
Because we have 3 and then 920
What
and
was
then
the error?
2 for 9. Oh, whoops.
Or do you want to see what the error was? Maybe there's one more null?
3, 920. Null, 15, 7. Null. It's supposed to be. No, never mind. Null. 14, null.
Or maybe no nulls after 14? Yeah. Oh, no. If I do 16. It's the line address. I don't know what I'm doing.
Copy the original one and see if it still works. No, never mind. That'd be dumb.
We can just do this too. So if we go, oh,
You can't add null to null.
no, wait, no, there's, maybe it's because it's unbalanced at that point, too far, but that shouldn't matter because it's a, maybe you don't need it. Okay, you don't need the nulls. That's why. So once the null, I guess if it's null there, then you just go down the next one. So C4,
Hmm.
if you want, you can do. So whether it's 14 or 16, we're still driving down to the lowest point.
Oh, duh, because it's doing. Oh no, I see. Oh, I see. No, I see why.
Yeah, because it's what it's doing is essentially, this is what you're seeing. We start with going to the, let's say we'll start, we go to the right and we get here. We can go back down here and we get down to, we basically get to 3. So then we go down to the left and we stop. But see, the problem is that we've, this is our first time through, I should say. Let's do this. Let's do this the actual way.
Oh wait, hold on. Why is it int right equals max steps when it does? No, hold on.
Because max depth is
Oh,
returns an
okay.
int. That's why.
It produces an.
So essentially, our first look through,
Okay.
when we go here, we just see that. But we're not really stopping when we only go 1, right? Because now all of a sudden I'm here. When I hit left, when I hit right here. So as I start again, I'm going to go through, I move down, each one going through. I'm now at 9, 20, nothing under 9, so I stop. 20, I'm going to go and then I find the next 2 coming down. Did you apply to Amazon?
No.
Do you have any other questions on these?
On this one, no. Oh, I mean, I'm trying to work. I want to work through the recursion. I don't know how long it's going to take me.
What's that?
Nothing.
Yeah. Because I got through the first phase of the Amazon test. That's why.
Oh, yeah. No, I don't think I applied for Amazon. I looked up. Well, because I was in trash class today. Hold on. Let me get rid of this chat and this better. I was in trash class today doing trash stuff, and I found another 3 interesting looking LinkedIn things. One of them worries me because one of them looks pretty cool. It's FDM. Oh, wait, no, is it FDM? Yeah, FDM, because FDM doesn't necessarily state which language they're interested in. because they're looking for a software. Oh, I just read the full words. Never mind. It says consultant. Oops.
So
Because some of the people I looked up today were like C and C# and C++, and I don't know that.
yeah, okay. So the Amazon, and there is recent graduate. It's in Austin. So you'd have to either move or travel. But
You
the
have to
first,
what?
so the first round is just debugging code.
Oh, I like that.
So the key piece of, and oh man, this was actually one of the problems that I got. That's good. This is
Despite
actually one of,
maximizing the screen, I still can't read what it says without putting my face to the screen. Check pair sum exists.
here, I'll put it in the chat. This is the,
Oh, I have to open the chat. Yeah, give me that. Stop annotating this.
so from there,
Oh no, a set.
but this was
Yes,
this was a pretty easy one.
Yeah, if that's a pretty easy one, then that's not good for me. Code debugging, coding and work style, stay in the life. SD simulation. Ooh, fancy.
So you get to compile and run the code as many times before you need to submit it, and you can skip questions too. So the key piece is on line 19 of this one.
Oh, am I supposed to be solving this?
Well, I mean, I'm just pointing out where the error is
Where did you say it was?
on line 19. Because as you go through, okay, so we're checking if the pair sum exists. So we're going through our matrix. So we got our rows and columns. Everything is correct on these two loops. And then we're checking if the set contains the sum minus the array at I and j. And if it's there, it's true. Okay. Else, if this doesn't if the set doesn't contain this, then we're adding sum. Well, what is sum? Sum is just whatever number comes in. So we're never ever going to be able to check if it contains sum minus array because we're not adding that in there. So sum is not what we want to add there because our set doesn't have the sums. What we need to put in our sum is our array. So instead of sum here, we end up putting this.
Oh, whoops! I'm not looking. I'm looking at the.
We're just putting in array I,
Oh.
j. And now when you compile it, all of a sudden everything works. So it's not. So there was like two hard ones that I don't think I solved correctly, but because I didn't solve them. But there's like 7, and I know I got 5 of 7. So. And most of them were like the curly braces were in the wrong spots, or or the variables were not doing what they're supposed to do. So
You could have just used the shortcut.
So it's not that it's challenging because of 2 or 3 of the problems, but it's not like impossible.
Yeah, for you.
We'll just practice a little bit. That's all. And there are practice sites out there, so just for this.
Like what? Like LeetCode?
No, there's actually like if you like Amazon debugging, you can Google and there's practice tests out there.
Oh, what if like a company that's like not, top 500? Or what Fortune 500, whatever they call that.
Oh, that's hard to find a non-Fortune 500 company, man.
Well, most of
Unless
I
you're
don't even
doing
know
like a startup.
I don't know what half these companies are that I've applied to. Most of them aren't like big names. Some of the LinkedIn, I mean, I'd never heard of them.
Like what?
Well, let me see. I don't even remember what some of them. I applied to something called HCL.
Yeah, the one I gave you.
Actually, did I? I don't know, because like one of
They
these
did
gave
it-
me like a really weird like response, like when you had to. I don't know which one I was applying for. It might have been IBM. I think I applied for IBM, or I tried to apply for IBM, but it said you need to sign in as a user. I'm like, well, I never created a user, but there was no sign up page on that page, and there's no sign up page on their website. I was very confused. I signed up for something.
Yeah. Did you sign up for
I don't know.
to talk to HEB on Thursday at the career fair for TAMUSA?
Oh, can I create an account like this? What? Sorry, what?
Did you sign up to speak with